Bismillahirrahmanirrahim. Welcome to the online class. Today's topic is generating FM waves. The course title is EEE 351352 Analog/Principles of Communication System. Here I am Dr. Ishan Khalil from ECE Department, CUIWA campus. Okay, let's move to the lecture contents. In this video, we will study in detail how to generate the FM waves. And there are two methods to generate this FM wave. First one is called the direct FM wave, direct FM generation, and the other is called the indirect FM generation. So we will study these topics in detail in this video. Okay, first of all, we will discuss what is direct FM generation. Like how can we directly generate the FM waves? So it is a simple method where carrier frequency is directly varied by the message through voltage controlled oscillator VCO. I think you have studied this VCO in detail in some other courses. So you can directly generate carrier from a voltage because message is a voltage. So using that voltage we can directly generate carrier frequency using a voltage controlled oscillator, because that voltage controlled oscillator means that based on the voltage of a signal it generates the oscillation. Oscillation in other term is a frequency. So voltage controlled oscillator output frequency changes linearly with the input voltage. Like there is a relationship between output frequency and the input frequency. When input voltage. When input voltage varies, then in the linear proportion, output frequency also varies. So to implement the VCO, the simplest one is by a variable capacitor. It means that it will change the capacitance of a circuit in the output. The frequency will change. So, for example, capacitor microphone FM generator. This is capacitor microphone FM generator. It means that it has varying capacitor inside. When sound waves impinge on this capacitor, then what happens? It will just change the capacitance of the capacitor, and in the output, the frequency varies. For example, this capacitance varies, and it will varies the output frequency, and we have the final output frequency here like a radio waves. So this is the simple generation of a FM signal using a variable capacitor, right? Let's move to the next slide to see further details. Okay, the main advantage of the direct method is simple. What is direct method? Just we discussed that we just put there is a wave that is a voltage, and we just uh, send it to the capacitor, and the capacitance varies, and in the output we have a variable frequency. So this is called a direct method, and it is a low cost but lack of high stability and accuracy. The problem is that in direct FM modulation there is a lack of stability and accuracy, and low power application, and unstable at the high carrier frequency. So when we have a high carrier frequency, then this method is very much unstable. So we have to ignore this method. So capacitance changes with the applied voltage. For example, this is the voltage capacitance equation. This is your output capacitance. This is time dependent, and this is some constant capacitance, and this is the change in capacitance delta C, and this is your message signal. So when message signal changes, then the final output capacitance changes. So you have seen that the oscillator frequency depends on the capacitance. I think this you have studied lot of time. So you can calculate the frequency using 1 over 2 pi LC. So this is LC tuned circuit. You can just use this tuned circuit to generate the frequency, and the frequency depends on L and C. So just put these C values here. We just calculated here. So put it here. So it becomes LC naught plus L delta C MT. from here we can clearly notice that as capacitance varies, frequency varies in voltage controlled oscillator. So this is a simple relation which can be easily understood that by varying capacitance or by varying voltage, capacitance varies, and in the output frequency varies as well. So in this way we can generate the FM signal, and this method is called a direct method. Now let's move to the indirect method. This is a very much practical method, and in the current systems, most of the system have adopted indirect FM method. So how this indirect FM method works, let's move on. So first of all, generate narrowband FM. We need to generate the narrowband FM first, and then it's multiplied by a targeted multiplied some factor to achieve the targeted delta F, means the frequency deviation, and the carrier frequency. So good for the requirement of a stable carrier frequency. So indirect FM is very good to generate a stable carrier frequency, and it is commercial level FM broadcasting equipment all uses indirect FM. So in commercialized equipments where we are using FM modulation, all are using indirect FM method to generate the FM waves. So a typical indirect FM implementation, Armstrong FM modulator. And the block diagram of indirect FM, we will study Armstrong later on in detail. So let's move to the general block diagram of indirect FM modulator. So look at this. This is your message signal that we need to modulate for some carrier frequency. So first of all, we will pass it to the narrowband FM modulator. So this is our narrowband FM modulator, because it has a stable crystal oscillator frequency. So in output we have a voltage VT, we have an output narrowband FM modulated signal. This is our narrowband FM modulated signal, right? So to obtain the desired frequency, because narrowband means there will be a small bandwidth and we have a small range of frequency. We can't generate a high carrier frequency by using a narrowband FM, because there is a condition we can only have a very less than one modulation index. So in this case we can't generate a high carrier. So to generate this, we just pass the narrowband FM generated signal to the multiplier, n times multiplier. N depends on the selection of n depends on our targeted carrier frequency and our targeted delta F. So our targeted delta F and targeted carrier frequency. So selection of n depends on this. So NFI, it means that this frequency, input frequency into n, we will get the final frequency here, the desired frequency and the desired frequency deviation. Okay, there is a steps which we mentioned for indirect FM generation. So as we mentioned earlier, that first of all we need to generate the narrowband FM signal with a very small beta 1. Like beta of a FM, narrowband FM, we already studied, is less than, very less than 1. So it should be a very small value, right? And this is the general equation of the narrowband FM, right? AC cos 2 pi ft minus beta 1 AC sin 2 pi ft, right? So this is our general equation into sine 2 pi fmt. This is our message signal, right? So for example, this is our message, this is our narrow band over a narrow band FM block, right? And we need to modulate this signal, right? This is our message signal. We need to modulate this one by using narrow band FM. So this portion, which I circled, will generate the narrow band FM, right? How it generate? It is, for example, AC cos. We will have a AC cos 2 pi f1t here at this point, right? This is a mixer, and when it passes to the minus 90 degree phase shift, it will generate a sine wave. So AC sine 2 pi f1t, right? So here we have a message signal. So it will multiply with the message signal. So for a message signal, we took this sine 2 pi fmt. This is our message. So this sine and this sine will multiply. So we have a sine 2 pi f1t sine 2 pi fmt, and the beta is the gain of this amplifier, and the AC is the carrier amplitude. Here this is mentioned, right? So AC mt minus beta 1, because we are subtracting here, right? So at this point it will be subtracted. So AC cos 2 pi ft, that will come here directly, and minus this one. So we will get narrow band FM signal here, right? I think there is a typo. This will be a summer, not multiplier, right? Sum, right? So if you have a summer block here, you can use this negative sign, generate negative. So summer or subtractor, we use this same sign, right? So AC cos from here, right? AC cos from here, and then shifted version is the sine 2 pi, message from here, sine 2 pi fm from here. So these two multiplied when come here at the subtract. So we have a narrow band FM signal for a message signal sine 2 pi fm. So this is the general block diagram, and you can say that this is the extension of this block diagram, right? Okay. After getting this, then apply the frequency multiplier to magnify beta. Now the next step is that we need to multiply this, we need to enhance the beta to get the wideband FM signal, right? So what we need to do, we have to multiply with the frequency multiplier. We will discuss this frequency multiplier in detail in the next coming slides. So instantaneous frequency is multiplied by n. So if you have a frequency f I instantaneous at that one, so it will be multiplied by n. So do the carrier frequency delta f and the beta. So in other way, you have the fc will be also multiplied, and beta will also be multiplied by passing through this multiplying factor multiplier. So for example, Vt, so this to generate the NFI, this is a non-linear device, right? This non-linear device generates this NFI, right? And in the output we have NFI, then we pass to the band pass filter. The reason for using the band pass filter, because there will be number of components. This non-linear device has a expression which we will discuss on the next slide, which generates the number of components. For example, linear, squared, cubic. So we need only one of them. For example, our target is twice the instantaneous frequency, twice the instantaneous frequency. So we need to filter the others. For example, this is our FM signal which we need to transmit. Right, that this is the narrow band. When we pass through the non-linear device, it will multiply by NFI, so it will be there will be number of terms, right? They didn't mention plotted right in this way. There will be number of terms. So, but we need this carrier frequency, right? FC is NF1. F, for example, N can be 3. So 3 F1, right? So we need to ignore the 2 F1. This is 2 F1. This is F1, right? So we need to ignore these terms. So to ignore these terms, we use the band pass filter. So this dotted line means filtering. So after filtering, we can get the desired modulated signal. So this is the mathematical analysis of the indirect FM. This was our input, right? The general equation of narrowband FM, where instantaneous frequency is F1 KFMT, and the beta is the modulation index, which is maximum of KFMT or over W, right? Or usually we called it as a delta F over W, right? Or FM. So second step, non-linear device. When we uh, input this narrowband FM generator to the non-linear device, then it will generate NF1 plus NKFMT. This is the expression for the non-linear device output. They generate the linear, squared till n term. So we need the one of these n terms, so we need a filter. So to filter out band pass filter, select new carrier frequency, which is NF n can be 2, 3, 4, which is our desired. So we will get this term, right? Where now fi is nf1 plus nkf, similarly beta is nkfmd over w. So this is again the similar block, nonlinear device, band pass filter. We get the output signal here. So this was the mathematical description or analysis of the indirect FM. So now, before moving on, we need to discuss some important concepts. For example, one is the frequency multiplier and the other is the frequency mixer. What is the difference? So these frequency multipliers are the non-linear devices with band pass filters are known as the frequency multiplier. So when there is a non-linear device with band pass filter, it is called a frequency multiplier. So by passing a signal through it, both the frequency deviation, when you pass the, for example, this is our block diagram of frequency multiplier, or we call M, right? When you input here frequency delta F, signal with some delta F and signal with some carrier frequency FC, right? So when you pass through this multiplier, it will multiply both N delta F, right, and NFC. So change both the deviation and the carrier frequency. So deviation and the carrier frequency by integer n. So if we want to increase 12 times the frequency deviation, then we can use 12th order non-linear device. So we can directly use here 12th order non-linear device or 2 second order and 1 third order. For example, 2 second order, 1, 2 and 3. So we can get 2 into 3, 12. So same factor. So it depends on the availability. Usually they suggest that you have only 2 multipliers and maximum 1 triplet. So you can only adopt this combination. So this combination depends on the availability of the types of the multipliers. The other is the frequency mixer. So frequency mixer, by passing the it is difference from the difference, main difference between the frequency multiplier and the frequency mixer is that when you pass the signal through it, it means the frequency mixer, only the carrier frequency change where the frequency deviation remains constant. For example, this is our mixer, right? Mixer. So when the signal is input here, two signal, right? This one is, so when the signal is input here with the delta F and FC, right? Any frequency. Here you have the same delta F output, but the carrier frequency will be changed based on the factor, right? NFC, for example. So in frequency mixer, the deviation remains the same, but the carrier frequency changes. However, in frequency multiplier, both deviation and the carrier frequency changes. So these two blocks are very much important to discuss the basis of Armstrong FM modulator. So Armstrong designed his FM modulator, which is very much practical and adopted nowadays. So these two multipliers and the frequency mixer will be used frequently over there. So you must have the understanding before going to the Armstrong FM modulator. And Armstrong FM modulator is also indirect FM generation method. Let's discuss the Armstrong FM modulator. So in Armstrong FM modulator, it was invented by the Armstrong and it is an indirect FM modulator. A popular implementation of commercial level FM. So in commercialized FM, this Armstrong FM modulator is used or it's adopted. So for example, you need a final output 91.2 megahertz, right? And the carrier frequency and the deviation is 75 kilohertz. So we need to design the Armstrong modulator which can generate this carrier frequency and this much amount of deviation. So before going to this, we need to begin with the narrowband FM with a carrier frequency of 200 kilohertz. So this we selected this carrier frequency because the reason of selecting this carrier frequency is easy generation using the stable crystal oscillator. So this we will start with the narrowband FM, and the narrowband FM is 200 kilohertz. So to maintain beta less than 1 as required in narrowband FM, we started with the delta f is equal to 25 hertz. So our targeted delta f is 75 kilohertz, and we started with the delta f of 25 hertz. As you know that for tone modulation, delta f over fm is the beta. So whereas the baseband signal frequency ranges from 50 hertz to 15 kilohertz. So the upper bound in the first possible case, if we put the 50 hertz in this equation, right? So this will give us the maximum, because this one minimum, then this one will be the maximum. So if we put this one here, so we get the beta is equal to 5. Uh, the choice is reasonable because it gives the beta 5 for the first possible case 50 hertz. So if we put 50 here and delta f 25 here, so it will give the zero point 0.5, so which is the worst case. So it looks, the selection of delta f looks reasonable here, right? Okay, now let's discuss in detail the block diagram of Armstrong and the how we generate the desired output frequency. So that to achieve the desired output frequency of deviation of 75 kilohertz, it means that we need, at this point we need delta f equals to 75 and the carrier frequency 91.2. So this is our output point. So we need a multiplication to generate delta f at the output. We have an input of only 25 hertz. Look at this. This is input, right? And this is carrier frequency, 200 kilohertz and 25 hertz. So delta f we need at the output 75. So we need a multiplication. For example, 75,000 over 25, 3,000 multiplier times multiplication. We want to achieve 3,000 factor of multiplication. How can we achieve? This can be achieved by two multiplier stages. One is of 48 and the other is 64. For example, this is 64 and this is 48. So we need a two multiplier stages, because when you multiply by 48 and 60, we roughly get 3000. It's 3072, but we can't generate exactly 3000 because of the limitations of the doublers and triplers we need to adopt. So for multipliers, we can adopt doublers and triplers as well, as we already discussed. However, these multipliers also increase the carrier frequency. If you see that when your carrier frequency will pass to this multiplier, for example 200 into 64, it will increase the carrier frequency to 12.8 megahertz, right? If we keep multiplying again like 12.8 into 48, then we'll further increase to the carrier frequency to around 600 megahertz. But it is not desirable. We need a 91.2 frequency at the output, right? So for this we use a frequency mixer, or this one, frequency mixer or frequency converter. What will it do? Does it will when the frequency here after passing the 64 multiplier is 12.8 and the deviation is 1.6, this converter will not change the delta f2 value, right? It will keep constant 1.6. However, the frequency is 10.9 and when it 12.8, so difference is 1.9. So 12.8 minus, we will have minus 10.9, so we will have around 1.9 megahertz of frequency, right? So when we pass it to the multiplier of 48, it will generate around 91.2, which is our desired frequency, right? And the same delta f is around 76.8, but our desired one is 75. So this is the process of getting the desired carrier frequency and the desired frequency deviation using Armstrong modulator, right? There is a one example in the book. Example number is, I think, example is 5.7. So you should do this example to get the better understanding of Armstrong modulator, right? Okay, thank you for listening. And for question answer, there will be a separate online session. So the exact date and time will be communicated later on. Thank you.